Hey, it's Alex Williams of the New Stack. Hey, we spent a week at Intel Developer Forum in San Francisco recording podcasts about scaled-out architectures in a multi-cloud world. Thanks to Intel for having us a part of the show and the chance to explore more deeply topics such as telemetry, orchestration, and the new dimensions that come as software and hardware more deeply integrate in a scaled-out world. You can learn more about Intel at intel.com. Okay, Alex Williams of the New Stack here at Intel Developer Forum. It's really the first day of the conference, and here with Brian Womack. Hey, Brian, how are you?
Howdy. Nice to meet you.
Brian, you're in engineering at Intel. Can you tell us a little bit about what you do there?
I work in the software-defined infrastructure group, and I'm responsible for doing distributed analytics in that space. We want to help make the next generation of SDI more effective and easier to use.
So distributed is a word we hear a lot about, right? What is the difference that you see when you're thinking about distributed analytics versus just traditional analytics?
So let me set a little context. We introduced a term here at IDF called software-defined resource, an SDR. There's 4 different types: processor, memory, fabric, and storage. And people who manage data centers have collected telemetry in the past to try to observe what software-defined resources are doing, and some aren't software-defined. And so then you can do something about it. You want to do some kind of action. You want to do something about your capacity. You want to solve a problem. You want to make an application perform better, etc. Well, one of the things, if you want to scale, you want to really distribute your analytics. By that, I mean you want to avoid moving all that raw telemetry data to one place and then doing the analytics. Instead, you want to do as much of the analytics on every node or as close to the nodes as possible so that you're not swamping your management fabric with raw telemetry data. So you can compress the activity with activity features. That's what we're showing in our demo at IDF. By 1,000 to 1,000,000x, depending on what they are, to summarize what's going on. So, for example, if you're just trending soft SLAs, you don't need to store all the raw, super detailed telemetry. You just need summary data, what happened the last hour or 5 minutes, and then have a highly compressed representation of that.
Okay, so so distributed analytics really is a term too that has its roots with thinking about, platforms that use Hadoop, for example.
Sure.
Right? What is the difference now as you think about the analytics on the node itself?
So you can think of Hadoop as a coarse form of distribution, where you take an algorithm that is potentially inherently single coherent memory space oriented in its thinking and its assumptions, and then puts it in a platform that, yes, makes it run on multiple nodes, but maybe not as efficiently as it could be. You see some problems with that in some of the first machine learning algorithms that were moved to Hadoop. Weren't really refactored. They were just moved to Hadoop. Yes, it performed better, but you're using a lot more hardware than you probably needed to. Efforts like Spark, they've attempted to optimize that and change it, but it's still using that same underlying architecture. If you want to take distributed analytics to the ultimate level, you do it more of an HPC approach, where you're literally avoiding communication you don't need across the fabric as much as possible at every step.
Okay, you don't need across the fabric as much for every step. Why?
Well, think about it. If you are doing, much machine learning involves matrix operations.
Yeah.
So if you're doing a matrix operation that requires a lot of copying back and forth across rows and columns and diagonals of the matrix, that's a lot of data moving on your fabric, right? Instead, if you were able to potentially tile a matrix to split it into smaller pieces, maybe each node could operate on one tile, then you're avoiding a lot of that communication traffic entirely. That's just one example of a distributed data structure to facilitate that. Other machine learning algorithms aren't that simple. You can't just split them into tiles. So you can imagine using the new memory that's coming online, like 3D XPoint, where you have much more memory on each node. Maybe you take 9 times the memory on each node to, again, provide context about what you're doing in the compute around, everything around one cell, but you're avoiding the fabric communication in the process. It's that kind of refactoring that is occurring in the analytics community. There's a lot more that needs to be done there.
So you touched on these new machine learning algorithms and the advent of new memory technologies. How does that play into then the analytics that you're doing itself?
Well, just when it comes to telemetry, it's just the idea, right? Is that you want to have the compute be as distributed as possible. You don't want to move the data more than you have to. And so that informs the telemetry analytics space, where its goal is to observe software-defined resources to know what they're doing. So if you have several applications running in a cloud install or an HPC install, you really know what's happening. And you see a performance problem, a capacity limit, what Google calls the red line, is reached. Well, what caused that specifically? Was it too many memory reads? Was it a few memory reads but very large sizes? Was it lots of writes to storage? What was it, the exact problem that caused these two applications to interfere with each other? We introduced in our demo a concept of a red line, a yellow line, and a yellow line for software-defined resources. The red line is, if it's by itself, that's the limit of that one resource all by itself. A yellow line is two resources conflicting with each other that effectively make a red line if they both hit their yellow at the same time. And then there's even lower interactions that can occur that are not just a simple threshold based, where there's a lot of high frequency activity on a given resource that can cause problems. You can see that with caches and the behaviors in and out, where you can't just detect it with a simple if greater than 5 type rule.
Mm-hmm. Why is this more relevant now? I mean, there's the obvious reasons about the amount of cars that will be transmitting data, and just everything that we wear may be transmitting data. But what is it that some of the kind of dynamics that are making the need for this possible? Is it just like the sea of data that we're starting to see?
Well, I think there's 2 reasons why it's relevant now. One is the idea that there's going to be many more types of software-defined resources. That's going to make software more effort, for one. The second thing is everyone talks about big data and wow, we got to store X petabytes of data. And I'm like, well, do you really? If you do distributed analytics and you're able to summarize the activity in such a way that you don't need to store the raw data anymore, you could potentially store 1,000th or 1,000,000th of the data. So you think of a smart city where they're talking about having more robotic cars that are collaborating together. You can't send all the raw sensor data to one place. Forget that. There's no way. It's physically not possible. So you have to do it distributed on each platform and that they collaborate together in local regions.
So that's, again, that distributed capability.
Yes.
So tell us about the technology itself that you're using to do the analysis.
Well, our current focus is let's take telemetry data using Snap.
And explain Snap.
Snap is a framework that's open source to make it easier to collect telemetry. And we wanted to provide a layer above that can do analytics, make it easier to create actionable insights into telemetry data, to even tell you what to collect. So the example before I used of SLA trending, well, what telemetry do I need to do that well? And not just what telemetry, but what rate is it good enough to collect it once a minute? Or maybe summarize for a minute? What should I collect? Same thing for fault prediction. If I want to predict DRAM memory failures, what telemetry do I need to collect for that? And what machine learning algorithms do I need to run? We want to provide some references to do that.
So you want to provide some references to do that?
Well, when I say references, I was a little vague. What I mean is software libraries, tools, best practices, reference architectures, maybe something in open source or, in the future.
So tell us some of the specific things that you're working on in that context.
So, when you look to collect telemetry, you want to summarize the behavior. There's a lot of work that needs to go there. There's signal processing,
Signal processing
gears. You need to crank. You got to be able to do frame-based processing. You have to have code that can perform on collections of frames, to summarize it, to do analytics on it, to say, I have these 200 pieces of telemetry, which 10 or 20 are the most useful for the business mission I'm trying to solve.
So how's a frame defined then in your context then?
So a frame is a period of time. So you can imagine raw samples, let's say they're collected once every second. A simple frame could be a 10-second frame that has 10 samples.
Right.
You could have one that's an hour or a day or a week or a month.
Right.
Well, how do you know how long to collect a frame for? Is it okay to have a mean over a frame of a 10 minutes duration? Or should it be an hour? Is the mean even the right thing? Should it be the minimum? Should it be the maximum? Standard deviation? What about spectral features? That captures the fuzziness of the signal. You might want to say, what's the ratio of high frequency to low frequency behavior? That could indicate, for example, on the error correction rate on DRAMs, that could indicate a coming fault when that behavior starts to go up. Things like that. So, there's just a lot of plumbing there, and if we can provide that to the community and make it easier for them to do, it'll make it accessible. They don't all have to be data scientists or signal processing engineers to do it. They just say, hey, I want to do this, and it tells you what to do.
So are you providing that as libraries then, or how do you provide that?
We don't have plans to do that at this moment. Right now we're figuring out the details. There's a lot of work to do. I mentioned red lines and yellow lines. I think a service we could provide the community is, where is the red line for each type of software-defined resource? You could say, the marketing literature says this fabric switch has this bandwidth. Well, that's true, but when messages are certain sizes or certain number occurred in the past, whatever, the queue depth starts to get full and all of a sudden it's less. We want to build that in so that you don't have to be a hardware engineer to model it properly.
So one of the things that came up in the panel yesterday at the Intel Builders event was a discussion about the telemetry and what is involved in collecting that data, right? So you have the physical layer, the VM, the virtual layer, and then you can also have a container layer, right? So you have these three layers, and so you're having physical layer, then an abstraction on the physical layer, and then another abstraction in essence with the container. That makes it, I think, quite complex to understand even what data you're getting out of it and how to really analyze it, because just to understand kind of that whole system itself is quite extensive.
Well, that's part of one of the goals Snap has, is to make it easier to collect at those levels. My job is to create activity features that summarize what's going on across levels. For example, memory reads. I want to have a higher level activity feature that summarizes what's happening at the raw level, what's happening at the VM level, what's happening at the container level, maybe combines all three. Same thing for writes. But have the ability to drill down and say, well, okay, which of those three contributed most to the problem I had? That level of transparency is what customers have been telling me they need. And
okay, so let's say so you define some activities, right? What are some of the use cases that you're starting to find, and are these outlier use cases? Are you starting to have enough use cases where you actually know what the core ones are?
Yes, so several of our customers give us examples of workloads that behave badly together, or they say, we have a problem with this one running, and they'll give us code to try it out, and we'll run comparisons of multiple together to see, well, what is causing the conflict, and can provide recommendations to say, hey, don't ever run this one with that one, and use build that into your scheduler. I think the whole scheduler space needs to get a lot smarter over the next year, and I know we're going to put energy into that. If you can observe what software-defined resources are doing better with a higher fidelity, of course, you're going to be able to do a better job scheduling. I would argue that part of the problem with scheduling today is it doesn't have enough observability into what's actually going on, so it's constantly playing catch-up. So it's too coarse. So we need to make it a tighter control loop. It has to be, any control, if a system is going to be controllable, you have to be able to observe what the system is doing. obviously. If you can't observe it well, you're not going to do a good job of controlling it. Like for example, if you had a thermometer outside this building trying to control the temperature inside, it's not going to work very well, right?
No, that doesn't quite do it, does it? So when I'm thinking about schedulers lately, I'm thinking of like schedulers that you see in Kubernetes and schedulers you see in Mesos.
Sure.
The schedulers, are these the same schedulers you're talking about? Or these are different variety?
Yes, those, but I'm also thinking schedulers that control things in a more granular sense. So not just initial placement of jobs or VMs, but hey, container, here's how you should run, not just where.
Right.
Hey, I know you, because of your workload pattern, I know you read memory freaking 10,000 times, and that other workload only reads it 100. So I'm going to give you the high bandwidth memory.
So that's the big challenge right now, is understanding the workloads that are running and best optimizing those workloads.
Right. And that's part of where some of the research going on, we're working with Intel Labs. Really, let's create a better workload signature that captures things like I just said. And then once you have that, you can say, oh, this one reads memory a whole bunch of times, and it reads big, it's this about this size. So yeah, that fits in the high bandwidth memory I have, so I'll put that on a night's landing.
So you use a good analogy with a thermostat. If you're using a thermostat outside to try to measure the internal temperature, you're not going to get anywhere, right?
Right.
So, considering that it is still pretty coarse in terms of the granularity that you can get, how does that analogy relate to kind of the work that you're doing? Like, I would think of it like an outside temperature gauge, right? It doesn't know like how cool the air conditioning is or what all those internal elements are. What is the work that you need to do to better understand, kind of what you're talking about in the context here?
So in an ideal world, the silicon would collect everything so we could observe everything. Mm-hmm. It'd provide nice summary features of what was going on, and then we'd all go home and be happy.
Right.
That's probably going to take a while. So there's a lot that can be done in the meantime. There's many types of telemetry that indirectly observe what's happening, and that's good enough. So you can see these other things occurring that tell you something about this other thing you can't directly observe, and that's okay. I've done a lot of that in my background. So.
Right. So what are some of the kind of the elements that you're trying to better collect so you can have those better data points for the analysis?
Well, you think about some of the telemetry the way it is today sort of depends on polling. You have to keep asking it, what's your value, what's your value, what's your value? And it's like, that's kind of silly. Wouldn't you rather have more of a digest type telemetry where it says, here are the basic stats for what I did the last minute?
Right.
And here's the min, max, standard deviation, maybe something else.
We're talking to people now more who are using like, some people call it data streaming middleware. In the context being that, using technology such as PubSub, you can start to develop subscription mechanisms for getting the data itself, right?
Sure.
So then you can start to be able to measure events more closely. Is this in line with what you're exploring and what you're looking at, or is it a different context entirely?
So we've talked a lot about telemetry, and I've talked about applying distributed analytics to the telemetry problem.
Yeah.
My not so secret other job is making scientific computing more effective and HPC, bringing the best of HPC and cloud together.
Right.
And I see all this contributes to that goal. There's fundamental building blocks in much of scientific and engineering computing that crosses many domains. So the idea of frame-based processing in Windows, that shows up all over the place. Doing that well, doing statistics on that well in the time and frequency domain is huge. If you can make that easier and make analysis of that data easier, then it just helps all kinds of applications. I mean, you just picked one.
Right. Well, what is the next 12 months looking like for you? What are some of the themes that you'll be interested in following, and the discussions you'll be wanting to pay attention to?
Well, I think the biggest thing I want to impact the community with is answering the question. So great, I have all this telemetry data I could collect. Really tying it to the business missions you have, and say, okay, for this business mission, you need to collect these 10 pieces of telemetry at this rate. And if you do that, here's some derived features that summarize that low-level telemetry well for you, even for a human to look at. That's great. I think that would be a huge accomplishment, just getting that done. And also establishing for each software-defined resource, what are the red and yellow lines?
Right.
What other resources impact this resource so that its yellow line becomes red? I think that's going to be a challenge, and it's something that we should be able to help with.
What is the challenge in finding kind of those line, that intersection with those lines, so you can get that data to that red line?
What are the challenges of it? Well, the harder resources. I mean, it's a constrained resource, right? And you could say, well, I want to know what every single thread in every application is doing. You could do that, but in an offline manner today. But many cloud operators, they don't need that level of detail. They just know how many jobs can I run at once, how many VMs can I have on one node, what character do they have, can I somehow summarize that in a way that helps me assign those resources well. I see that as the low-hanging fruit on the short term. The ultimate is getting everything down to the thread level, but that's going to take some, I think, new silicon to observe at that level, at least live anyway.
Well, Brian, thank you very much for taking some time to talk with me today here at the Intel Developer Forum.
Thank you.
Great.
Bye.
We spent a week at Intel Developer Forum in San Francisco recording podcasts about scaled-out architectures in a multi-cloud world. Thanks to Intel for having us a part of the show and the chance to explore more deeply topics such as telemetry, orchestration, and the new dimensions that come as software and hardware more deeply integrate in a scaled-out world. You can learn more about Intel at intel.com.